Hey, stay here, bro. Tyler. Tyler. Stay here because we'll talk about the project. Hey there. How are you guys doing? Thanks for coming back. So first homework's due tonight. How many of you have finished the first homework? Wow. Yeah. Yeah, round of applause. It was a little bit on the longer side, I will admit. Hopefully the rest of them should be shorter. Projects will be, of course, a little bit longer because they're 2 weeks. On that note, the first project is assigned today, so it's pushed onto GitHub right now. You can go and look at it right now, and Rohan will talk a little bit about it.
Okay, guys. So today you're going to learn about linear regression. Jordan is going to be lecturing. So the first project is really going to be a culmination of visualization and regression, along with some data cleaning. So you're given 3 data sets. You can choose any which one you'd like to explore. And the first part basically is to do some data cleaning, understand the data set, clean it up so it's in a format that you can use it in, and then from there you can generate your visualizations. And I'll ask you to do a couple of regressions, one linear and one logistic. So keep in mind, for this project, you have to be in groups of 3 to 4. So you can't be pairing up, or you have to be in groups. And the main part of this project is that there's a write-up. So you basically, I'm not giving you a notebook or anything. I'm just giving you a document that tells you all the stuff that you need to be doing and the specifications. You are gonna type up a notebook to explore the data, create the visualizations and regression yourself. But the main part of this is doing the write-up. So explaining your thought process behind all the steps that you took, all the choices you made, and kind of detailing all that in a write-up and explaining your findings at the end. The write-up is not supposed to be super intensive or anything, just a couple pages. Don't freak out about it. Once you have the notebook, the write-up should be pretty easy, just writing out all the stuff that you did. So it's not that hard. Don't freak out about it at all. But yeah, so you should submit to Gradescope your write-up, and after that, your PDF of the notebook attached. And it's all in the instructions. So I just wanted to give you guys a quick heads up, and that's what's coming. So this project is due. You have 2 weeks to do it, so it's due next Tuesday. Yeah.
Thanks, Rohan. I have 2 more things to say about the project. Don't include code in the write-up. Don't do that. Second thing is, I'll give you some time today to meet some people if you don't have a project partner. I'll give you some time during the attendance break to find some people to do the project with. And please, please, please find a group of people between 3 and 4. We won't take individual projects. Perhaps we'll take doubles if there's a really, really good reason why. But yeah, 3 or 4. Cool. So the last 2 lectures I've kind of gotten you guys up to speed with the not so fun part of data science, the cleaning the data. I think visualization is fun, but cleaning definitely to me is not too fun. And so starting today and going forward, we'll start to give you tools and methods and rules of how to analyze data and mainly do prediction. That's what we're most interested in, is prediction. So today I'll be talking about one of the most fundamental algorithms in data science. This is the basis for essentially everything else that we'll talk about. And linear regression is an awesome topic because I didn't pull this down, but also because it's really, really old. And because it's really, really old, there's been a lot of cool theory and methods that have been developed on top of it that have really opened the doors for a lot of cool things in modern data analysis. So how many of you think you know of linear regression, or think you know about it? Raise your hand if you think you know about linear regression. Okay, so more than half of you, as I expected. It's a pretty elementary topic as far as data analysis goes. You learn it in most algebra classes, at least. But I'm going to take a whole different spin on it and teach it from a machine learning standpoint, where we have data, we want to model the data, and we need to train a model to model that data. And there's a lot of cool things we can do during the training to make the model learn better. And so with that, let's talk about linear regression. So a little bit of an agenda of today. First, I'll give you some background, kind of get you guys all up to speed about where we are. Then I'll set up the problem and give you a taste of how we estimate these models that we're so interested in. And then something that is not talked about as much as it should be is the assumptions that we make when we do linear regression. Usually when you learn about linear regression, I'm guessing in most classes that you learned it in, unless you're a stats major, you haven't spent too much time thinking about why we can do what we do. And in the real world, a lot of those things that we assume aren't necessarily true. And so it's important to know what we assume, how to check for those assumptions, as well as what to do when they don't hold true. Next, we'll talk about model testing, where we'll discuss how do I compare different models, how do I decide which model is better than the other, how do I decide what variables to use in my model, how do I decide if a variable is even relevant at all, and those kinds of things. And finally, I wanted to leave you all with a taste of more advanced models. So I won't talk about a lot of the things, but I'll rather list a lot of them and briefly touch upon them to give you an idea of what's out there and what's being used in modern data science. So without further ado, a little background. So where are we? I like to think of prediction models or machine learning to find kind of four sections. And the four sections are further split up into continuous and discrete sections. And when I say continuous or discrete, I mean that the labels for my data are continuous or discrete. And so there's some examples down there. But the four types are regression, classification, dimensionality reduction, and clustering. So regression is all about predicting something continuous where I have labels for that data that I'm using. So that could be something like predicting housing prices. So suppose I have a bunch of data of housing prices, and I want to make a model that can predict the price of a house for which I don't know the house's price, based on the house's size, bedrooms, etc. And that's the regression problem because price is a continuous value. Whereas a discrete problem would be more classification, where I have discrete categories, where, for example, I'm giving a model pictures of dogs and cats, and I want the model to determine whether the image is a dog or a cat. And then later in the semester, we'll talk about unsupervised learning, where we don't have labels for our data. We don't know how much the house costs. We don't know in advance of whether or not the image has a cat or a dog. And so that's actually a very interesting field, and I think has a lot of the most potential and has some of the most potential to do a lot of damage in modern big data, where there's a lot of data, often messy and unlabeled. So that's where we are. And so I have labels, and labels can be things like prices, miles per gallon, price of a stock, a lot of things. And associated with this label is some explanatory variables, the X's. So the X's can include features about the data, which is labeled with the label Y. And so explanatory variables can be height, sales, engine power, anything that describes my data of interest, which is labeled. So in the housing example, the labels could be square footage, number of bedrooms, stuff like that, year built. And so the whole point of this class is, how does the computer make predictions? And that's what we're really concerned about. How do I make the computer make predictions a lot better than I can? So a lot of you think linear regression is kind of maybe basic or naive, but in fact it's very widely used. And for these reasons, it's very simple actually. It's fast, interpretable, and very powerful in what it does. There's a lot of nice properties that have been developed with it. And a lot of the stuff that we talk about today will not only be used for linear regression, but are kind of the basis for a lot of the other more advanced methods that we'll see later on. And lastly, it's practical. I mean, it's used all around you. For all you economists and physicists, your field is made up because of linear regression. Not entirely, but regression helps define some nice laws. That's all. So linear regression, here's the basic framework. So I have P predictor variables. So you can think of, just P of them. I'm trying to stay as general as possible. And I want to approximate Y, the output, as a linear function of the X's. So I have all my X predictor variables, and I weight them by some parameters, theta 1 through theta P. Thetas are called the parameters, or weights, which we need to estimate. We need to teach the computer to figure out on itself so that I can use it to make predictions. And the last thing I'll say on this slide is it's kind of common practice to introduce something called a bias term, where it's a constant it's not part of your original data set, but we artificially create x naught to be 1 as a bias term. And that allows a lot of things to work out nicely. Importantly, it allows us to write the model in this complex notation, the sum of the inner product of x transpose x. Actually, I don't think there should be a sum there, sorry. So, as we just mentioned, a little warm-up. Suppose I have the following data of house prices. I have all the prices of homes, the number of square feet in that home, the number of bedrooms, and I want to predict the price of a house from the number of square feet it has. So the linear model has the form like this. So the function takes in as input the square feet and outputs an estimated price. So currently the function that we have is a function of the square footage of a house. And it's a simple linear function with slope theta 1 and intercept theta naught. And that's our first linear model. We did it. We can all go home. But it turns out that it's a lot more complicated than that, and a lot more detailed and intricate and interesting also. So we talked about what the model looks like, but we kind of left it off at an arbitrary sense. We left the thetas as thetas, but we can't really use thetas to do anything unless we know what the theta should be, right? So let's find thetas, and that's where we talk about model estimation. So before I go on that slide, I just want to say that what we're modeling here, we're assuming there's some underlying linear function in nature. We don't happen to know what it is. We're not lucky enough to know. And so all we can do is put our best effort to estimate that function, assuming it exists. So in nature, we assume that the relationship between square foot and prices has this nice linear relationship with some true theta that's existing in nature that we have no idea what it is. And our best attempt at figuring this all out is to estimate it, what it should be, given some properties that we want to satisfy. And so now I want to talk about how we choose theta. How does the computer learn what the best theta is to use to make the most accurate predictions as possible? And so to do that, I'm going to start by introducing this in a little bit of not the standard way that you might have seen linear regression. I want to talk about something called a cost function. Who's heard of a cost function before? Okay, some quarter of you maybe. So a cost function is a way of quantitatively measuring our goal. And so here, our goal is to make an accurate model, right? So we want an accurate model. And so what we can do to make an accurate model is choose theta so that the function h of theta of x is close to y. If you can choose theta so that the function is close to the true value, then we're doing well. We're not doing too bad. And so this cost function, what it's doing is it's summing up the square differences between the true value, the true label, and what we predict it to be with our naive parameters that we don't know yet. And so, again, the goal and the heuristic is to be accurate. And we can be accurate by trying to minimize the residuals. The residuals is the difference between the prediction and the true value, the h theta minus yi. That's the residual. And it turns out it's more convenient to use the squared residuals. We're still minimizing with respect to the same thing, but if we're looking at the squared residuals, it turns out that that's just a mathematical convenience. You can also do absolute values of residuals, and you get different properties, but the most common thing to use is the sum of square residuals. And this cost function kind of gives us a cost about how bad our model is. And you can imagine that our goal is to have the smallest cost as possible. The smaller the cost, the less poorly we're doing. The better we're able to the better we're able to estimate the true function. And so again, to have an accurate model, we want to minimize j of theta. So now I'm finally using the word minimize. We want to minimize this objective function. And so I hope all of you have taken a calculus class and have remember your optimization, because it's going to come to play very importantly in fact, all of data science. So again, the idea here is to choose theta that minimizes j of theta. If j of theta is good, we chose the good theta. So that's the goal. And so one way we can do that is to use a search algorithm that uses the following scheme. So at first, I don't know what I should choose, so I choose a random guess for theta. And the goal is to continually update theta to make j of theta smaller. So I figure out how I should update it, and then I update it to make j of theta smaller. And I keep doing this until j of theta reaches a minimum. And once j of theta reaches a minimum, I found the best theta. That's the theta that minimizes my cost. and I'm happy. So a little bit of refreshers. So j of theta is, don't worry about it if you don't know what this means. It's a convex quadratic function, which means it has nice properties. It means it has a global minimum, which is very important. It means that we can actually find the best theta. That's the nicest property of convexity here. And from all of you Math 53 people, we remember that the direction of greatest increase is the same direction of the gradient vector. So the direction of the gradient is the direction of greatest increase. In our case, we want to decrease our function j of theta. So the idea is to, rather than going in the direction of the gradient of greatest increase, let's go in the opposite direction, the direction of greatest decrease. And if we keep going in the direction of greatest decrease, hopefully we'll reach our minimum eventually. And so the scheme that we just talked about is called gradient descent. And it looks something like this. I have my theta, and I update it by going in the opposite direction of the gradient times some learning rate. This learning rate is some value, usually between 0 and 1, and it tells me how fast I should be moving down my space to reach the minimum. So the larger the epsilon is, the faster I'll be approaching my minimum. But there are trade-offs between small and big epsilon, which we'll get to. But it's called a learning rate, and you'll see this over and over again. So this is what it looks like if I have two predictor variables. My cost function is in 3D. It's a 3D surface of two predictor variables. So you can imagine the x and y being theta 1, theta 2, and the z-axis being the cost. And the goal of gradient descent is to follow this red arrow until we get to the bottom of this convex function. And once we reach this at the bottom of this function, we found theta 1 and theta 2 that minimize j of theta. And that's our best guess at theta. So just a little bit of math. Don't worry if you don't follow this. This is just to, for those of you who are interested to know how this actually works under the hood. Feel free to follow along. But if this looks scary to you, also don't worry. This is not important to succeed in the class. But I do encourage people interested in data science to be well-versed in multivariable calculus, linear algebra, and probability. All very important for data science. But yeah, so the goal here is to take the gradient with respect to theta. And so if you do that here, you'll get something like this. And so the update rule is I update theta by subtracting y minus h of x times x. And if I keep doing this, I will find the best theta. But this is only with one training example. I only have one pair x, y, one training example with one label. I usually have more than that. So let's get into it. So in general, if I have p predictor variables, I have p thetas, or I guess p plus 1, but for theta naught, and n training points. So now I'm assuming I have n training points in p-predictor variables. And this rule of updating theta in this way is called the least mean squares rule. So I'm trying to minimize the sum of squared residuals, and so the name least mean squares makes sense. One thing we notice is that the size of the update is proportional to the residual term. So the h minus y, that part there, remember that's the residual term that we're trying to minimize the sum of squares of. And this kind of makes sense intuitively, because if the prediction h is close to the actual y, that means our thetas are probably pretty good. We're probably getting pretty close to the best theta 1 or the best thetas if my prediction is close to the true value. And so if I'm close to the right value, then I probably shouldn't update it much. So the smaller the residual, the smaller my update. Make kind of intuitive sense. And if we look back at this plot, we see that the closer we get to the optimal theta, the smaller the steps get. So a lot of machine learning algorithms can be framed as an optimization problem. And in this case, for linear regression, we have the following thing. While j of theta is not minimized, for each training point that I have, update the parameters in this way for each j, 1 through p. And that's stochastic gradient descent for linear regression. And it's stochastic because I'm using 1 point at a time. I'm using for each I from, sorry, let's just say 1 to n, not I to n. And I'm going through each point one by one and updating my parameters until j of theta reaches some minimum. So I talked about the learning rate, kind of how big our steps should be. And there's a trade-off, right? The larger the learning rate, the faster I get to my minimum. But it could be that my function is shaped in such a way that my big step sizes are causing me to miss the minimum. I could be bouncing around this saddle, this parabola, and missing the optimum by having such a big learning rate. And the trade-off with a small learning rate is, yeah, I'll probably get there eventually, but how long is eventually? I don't have all day. And so it's important not to pick an epsilon too small. And so there's ways to choose what size epsilon to pick, and kind of a lot of the rest of the class will talk about how we tune a lot of the hyperparameters that we talk about here. So here, epsilon, the learning rate, is called a hyperparameter, something that we choose ourselves, that the model doesn't learn itself. We choose the epsilon, and we need to figure out the best way to choose epsilon. And we won't get into that just yet, but we will later. Okay, so I'll want to stop there and just see if anyone has any questions. I know I'm moving pretty fast. So are there any questions about what we talked about so far? Yeah.
The Piazza page is open if you guys want to post questions on there. We're doing the same thing as last lecture.
Cool. Yeah, question?
How do you know you're not approaching a local minima?
So that's the beautiful thing of a convex function. Local minima are global minima. So if you found your local, you found your global, and you're good to go. Convex functions are great. Any other questions? Yeah.
How does epsilon change the theta value? Or like, how does what going to
Change the what values?
the theta value?
Sure. So epsilon just determines how big our step is. So it doesn't explicitly determine the theta values, but it determines how the theta values get updated. That's all.
As the data changes.
As the data changes. Not quite sure what we mean by as the data changes. The learning rate just affects how we update the parameters, or estimates for the parameters rather. Yeah.
Rather than initially finding a way to choose the learning rate, is there a way to optimize the learning rate already based on the initial set data?
That'd be very interesting. I don't think there exists such a method. Neil, what do you know about that? Is there a way to look at your data set and look at properties of your data set to determine an optimal initial learning rate? Yeah, that's not an easy question. I think that might be something people are looking into. That would be very nice to have, certainly, but I don't think it's something that I have an answer for right now.
Yeah, neither do I.
Cool. Any other questions before we go on to kind of a different way of looking at this? Alrighty. So the first way I talked about how to solve for theta, how to find the best theta, use something called gradient descent, which is kind of the basis for a lot of learning algorithms that we'll see going forward. It turns out that linear regression is, because of all its greatness, it can be solved in an easier way. We don't have to do this kind of complicating compute the gradient, update the parameters step by step. There's a way to find the optimal theta explicitly using calculus because of nice properties of the loss function or the cost function that we're using here. So in fact, there exists a closed form solution. We can find a solution that we can prove is the best theta. And we can do so by solving something called the normal equations. So recall the setup that we had before. We have an equation for a linear model that looks like that. And the outcome y, which we observe, can be thought of as a function of thetas and x's, or a function of x's, but parameterized by theta. And epsilon is some unobservable error, some error that exists because we can't know everything perfectly in nature. And again, we don't know what the true theta is in nature, so we estimate it with theta hat. And once we estimate it with theta hat, we can make predictions by plugging in theta hat into the above equation, plugging in new x's that we haven't seen before, and then getting predicted values. But let's look at this in matrix form. So rather than having one equation for every data point, I can kind of make this more compact by writing linear regression for all of my data into matrix notation. And it looks something like that. So each row corresponds to a different variable or a different data point. So if I have n data points, I have n rows. And the number of columns is the number of variables that I have. So I have p variables plus one bias column. So I have p plus 1 columns in this case. And then, so the vector y equals the matrix vector product of x and the vector theta plus an epsilon vector of errors. And capital letters will mean matrices, and arrows will mean vectors for our purposes. Okay, so back to where we were before. We want to find theta such that our estimate theta hat is accurate. And we can be accurate by trying to minimize error. And in this matrix notation, our residuals can be written as this. EI, the residual, the ith residual can be written as yi, the ith label, minus theta transpose xi. And so more mathematically, it's convenient to minimize the squared residuals. And it's more convenient mathematically, as you'll see in the next couple slides. So squared residuals is what we're trying to do. So our estimate theta hat is the argument with respect to theta of this sum of squared residuals. And so this is how we do it. So as we said before, our objective is to minimize or find theta that minimizes y minus x theta. In our case, the square root 2 norm of that. So the second line is just the first line rewritten. The third line is just some multiplications that have been done. And then I'm taking a matrix derivative, or I'm taking a derivative with respect to a vector. So my guess is that most of you haven't really seen taking derivative with respect to vectors before. That's okay. But that's what it looks like. Don't worry if you don't understand this. I just wanted to show you how I can solve for theta explicitly. And if you want to look at this more, the slides are posted, so you can just stare at this if you want to really understand it. I don't want to spend too long on it because it's not the most important thing for us right now. And so it turns out that the best theta is equal to this. X transpose X inverse times X transpose Y. And if you do this, if you do data science regularly, this is something that you should remember on, like you remember how to count to 10. You should remember the optimal theta in linear regression. Seriously, you could have, that could literally be an interview question. What's the least squares estimator? And then you'd have to repeat something like X transpose X inverse times X transpose Y. And then you would get the job. Cool, so we estimated it. We found the best theta. We're using calculus too. Yeah, question? Sorry? No, exactly, yeah. So for solving for theta this way, there's no actual learning that goes on. There's no iterative learning process. In fact, there's one explicit closed form solution that's written right here. And for all you people who love math like me, if you don't believe me that this is the best solution, you can take the second derivative and show that the second derivative is, here it's going to be the Hessian, the matrix of second derivatives, is going to be negative definite, positive definite, which means that this estimate is indeed a minimizer. So it works, yeah.
You would also, I think, see the result by using a bit of linear algebra and projection of it onto the space of
the column space of X. Yeah, so there's a lot of ways to look at linear regression. And it turns out there's a nice geometric interpretation. I'll briefly mention it for those interested, but this is, again, a little bit above. This is kind of something you learn about in the graduate class in linear models. But you can think of the predictions as being projections onto the subspace spanned by the columns of X, linearly independent columns. Yeah, nice geometry there. But yeah, not for us right now. So some facts. Like I said, theta hat is indeed a minimizer. Sure, that should say positive. Second derivative is positive. That's a typo. So that tells us that in our case, it'll be a matrix, and the matrix is the matrix of second derivatives is the Hessian, which will be positive definite, indicating that theta hat's a minimizer. Because of this long history of 200 years of linear regression, there's been a lot of mathematicians that have worked on kind of rigorous theory regarding this. And it turns out that theta hat is blue, which stands for best linear unbiased estimator. So out of all the unbiased estimators for theta hat from OLS, ordinary least squares, is the best one. And the word best means has the lowest variance. It's the least variable. It's the most accurate prediction that we can make for the real theta. And the last two bullet points are just because there's no reason I put them there. It's just to show you that what the residuals look like in matrix form. So the residuals look like that. And our estimate theta hat is not some fixed number. We estimate it, and then we get some numbers for our estimates, but those estimates are just realizations of a random variable. So theta hat's a random variable, and thus has variance. And so you can do various things with your estimate theta hat to look at its properties. And so that's how you would compute its variance like that. Don't worry about the last two bullet points though. Look at them if you're interested. Cool. So great, we talked about how to estimate a model, how to find the best model. Not find the best model yet. That's something we'll do in a little bit. We haven't done that yet. But now we're interested in using our learned model to make predictions. And so remember, we can plug in our theta hat into our model and then get predicted values for y. And matrix notation looks like that. And now this third bullet point is indeed the third bullet point, but it should be the first bullet point times 10. This third bullet point is super important. You have to know how to interpret your models. And so this is also something you should memorize along with the estimate, the closed form estimate. 1 unit increase in the kth predictor variable for the ith sample, we expect yi on average to increase by theta hat k. So sometimes yi will increase by more, sometimes yi will increase by less, but on average, we should expect it to increase by theta hat k. On average, that's super important. This isn't a causal statement. I'm not saying that a 1 unit increase in xik causes a theta hat k increase in yi. I'm saying that if I do it over and over again, on average, yi will increase by theta hat k for 1 unit increase in xik. So a lot of the times we take transformations of our independent variables, such as log transforms, square root transforms. And so if we take the log transform of the independent variable, the dependent variable, or both, then the interpretation changes and it involves percent changes. So for a 1 unit increase in this, y changes by this percent. So those are the kinds of statements we make when we take log transforms. And I won't go into that too much, but just know that that is a thing that exists. And so be careful when you're taking logs and interpreting your results. Cool. Assumptions. We kind of talked about a lot of stuff without talking about why we can do any of it and when we should do it and what to do if we can't do it. So let's talk about the assumptions that we made implicitly throughout all of this and throughout your whole lives, I'm assuming, unless you've taken a linear models class or econometrics or CS70 with scie. Cool, assumptions. So I've been talking up regression a lot, and it turns out linear regression is a great summary of the data, assuming some key properties hold. So for us as data scientists, we need to know what those assumptions are, how to test for them to make sure that they're held, and what to do when they fall apart. That's our job as data scientists. That's why we have a job. sklearn is pretty powerful. It can do a lot of the modeling itself. But the reason you see job listings for data scientists everywhere is because people like us need to know how to do things like this. So it's standard that there's 4 assumptions of linear regression. First one is linearity. We assume a linear relationship between the input and the output. We assume normality of errors. So the errors that we don't observe, we assume that they're normally distributed, as well as the residuals. The residuals should be normally distributed. We also assume homoscedasticity, which means constant variance, which means that for each x, the variation is the same. We don't have different variance for different x's. And the last thing we assume is independence of errors. So how do we check them? There's a lot of ways. Let's talk about linearity first. So like I said, we assume a linear relationship between x and y, which also corresponds to a linear relationship between y and the residuals. So if I were to plot a scatter plot of y and the residuals, I should see no pattern. If I see a pattern in a plot of y versus the residuals, then I'm kind of iffy about linearity being held true. So this is a plot that I made in R. Yeah, looks pretty good. Looks like the linearity assumption held. No trend, really. Maybe there's a ever so slight one, but nothing too drastic. So normality of errors. How do I check if my errors that I don't observe are normally distributed? Well, I can check the residuals, not the errors, because the residuals I observe, the errors I don't. So the first thing I can do is plot a histogram of the residuals. And if the residuals were indeed normally distributed, then the histogram should look like a normal curve, nice and symmetric, bell curve, bell curve. One other thing I can do is do a QQ plot. A QQ plot is I'm plotting the sample quantiles of my data against the theoretical quantiles of a normal variable. And so if my data does indeed come, or my residuals do indeed come from a normal distribution, then the sample quantiles should lie very closely to the theoretical quantiles proposed by the normal distribution. And so if the data was indeed normal, these points right here should lie on a straight line. And this, to me, is good enough. You can't expect perfection, but if your QQ plot looks like this, it's pretty good. If you see in your QQ plot kind of tails that are going up or going down, that tells you that your data is probably not normal, and there's some skew or other kind of shape that that's not good for linear regression. So if my QQ plot lies on a straight line, I'm good to go. And there's also many tests. There's something called a Magorov-Smirnov test, a Shapiro-Wilk test, and these are kind of more concrete statistical tests that I can do to check these assumptions, or this assumption of normality. So homoscedasticity, remember that that's the assumption of constant variance. And so a way to check for that is to also look at the plot of y versus the residuals. And I should see about constant variation as I move across the plot horizontally. So if I look here, I should look at the variation in this slice, and it should be roughly the same as the variation within this slice. And we do see that in this slice, it's a little bit higher, but overall, nothing too drastic that makes me worry. I'd say the homoscedasticity assumption is okay in this plot. And again, there's also formal statistical tests that you can do, such as the Bruce-Pagan test, a White test, and these are kind of more rigorous tests that we can do to actually get p-values and make conclusions as best as we can about these assumptions. So the last thing is kind of, I think, one of the hardest things to check is for independence of errors. And so one way that is really commonly used, and this is coming from time series, this plot, something called an autocorrelation plot, where I plot the correlation of a variable with itself over time. And I should see that most of the residuals should fall within this 95% confidence band. And if that is indeed the case, then I don't believe that there is some dependent structure in my data. Again, another test you can do is something called a Durbin-Watson test, and this is a very, very common one that's done for independence. And I will say that I know I'm throwing a ton of information at you, but I'll justify as to why I'm doing that. One, this subject is fundamental for a lot of other things. Two, there's so much theory that it'd be really shameful for me to just teach you the basics and not at least demonstrate to you all the other things that can be done. And then three, I don't expect you to internalize everything that I'm telling you. I expect you to be aware that these things exist, so that if you were to encounter these in your day-to-day projects or internships, you would know what to do. And that's the goal here. Cool. So now I want to talk about what do we do if those assumptions are not satisfied? If those checks that we did, if one of the plots fail to show independence, or one of the plots fails to show homoscedasticity, what can I do? And so for the first assumption for linearity, if the data is nonlinear, there's a few things I can do. So I can take a transformation of the data. So I can maybe take the log of all the data, or square it, or take the square root, and then perhaps it will become more linear. If the errors are not normal, turns out that this isn't as important as an assumption as the other ones, but transformations can help here too. Perhaps subsets of the data are more normal than others, so I might want to do some hierarchical regressions, where I look at subsets of the data at a time because it's maybe more normal in those subsets. And then outliers or high leverage points can also affect the idea of normality. So by having some weird points in my data set, it could make it seem as if my data is not normal, when in reality, if I remove those points, the normality is more or less satisfied. For heteroscedasticity, so that's the opposite of homoscedasticity. So if the data has heteroscedasticity, that's a mouthful to say, that means that there's not constant variance across the x's. Again, a log transform can be helpful here. So takeaway, log transforms, very, very good. Do log transforms. So you can remove outliers. That helps with heteroscedasticity here as well. A more advanced model might be able to model this non-constant variance structure more efficiently. So something called an autoregressive conditional heteroscedasticity model might be able to tackle that issue better. And lastly, it could be that this violation arises from violating one of the other assumptions. So maybe if we fix the non-normality, we can fix the heteroscedasticity at the same time. And finally, the last one that's the hardest to check for, but also the hardest to fix. If the errors are not independent, there's some kind of structural problem in your model. You're not modeling the right thing, and it's often very hard to fix. So one way you can go about fixing it that I'm aware of and have done before is something where I choose an appropriate ARMA model, which stands for autoregressive moving average, something that you might have seen if you've done time series work, and fit a generalized least squares model to this ARMA model that can take care of independence in its structure. So there's an example of the beauty of a log transform. I have this seemingly nonlinear data with perhaps heteroscedasticity on the left side, but if I take the log of both variables, I have a beautiful looking scatter plot. I couldn't ask for much else. So log transforms are nice. Cool. So we talked a lot so far. Next thing we'll talk about is testing, model comparison. How do I decide if I choose one model or the other? If I have all these variables, how do I decide what variables to use? What combination of variables is the best? How do I select my best model? What's my metric that I'm using? So that's what we'll talk about now. Before that, I just wanted to see if there's any questions. Yeah.
So in a lot of like physical systems, at least, there'll be like a large regime where they're linear, like it's almost perfectly linear, and then you have the extreme values where maybe the regime has neighbors off or something like that. Essentially, would you just split it into multiple data sets to deal with a linear regime separate from the rest? Or?
That's one way I think that could work. I'm sure there's other ways as well, but I think that's a very common sense way of going about that, is to look at subsets of your data that perhaps appear more linear and take the subset that appears nonlinear, perhaps because there are outliers or just non-conforming points, and try and model those separately, perhaps with a nonlinear model. Any other questions? Cool. Model testing. So we've talked for the last 40 minutes about estimating theta hat, but now we have some questions we should ask ourselves. And the first one is theta I, the ith parameter, is that significantly different from 0? Which is also another way of saying or asking, is the variable xi relevant? Should we be using xi in our model? Moreover, how confident are we about what the true theta is? How sure are we about our estimates? And the last question I think is the most interesting is, how do I know what independent variables to use? How do I decide if I have 1,000 variables about this data? How do I decide if I should use all 1,000 or if I'm better off using just 5 of them? Those are the kind of questions that we have. So to answer the first question, is theta I significantly different from 0? So for those of you who have taken a basic statistics course, this is what, or I don't know if you cover this in the basic stats course, but you can do some hypothesis tests and t-tests and f-tests to actually determine whether your estimate is significantly different from 0 or some other default value that you're testing against, some other null hypothesis. And I put a link here, Wikipedia link, just in case you want to read more about hypothesis testing for parameters. So how confident are we about what the true theta is? So maybe you've heard of the confidence interval. Linear regression is very nice because it's fairly straightforward to come up with a confidence interval for our estimates. Not so much in many other models, but for linear regression, it's pretty easy. So here's another link about confidence intervals if you want to look into that. And the last question, how do I choose what independent variables to use? Like I said, it's kind of more interesting, and so I want to spend some more time talking about that. So kind of a preface to all of this is, before we do any feature selection, before I decide what x's I should use, I should make sure to split my data set into a training set and a validation set. So I have my full data set, And I use some of it to train my model on, and I use some of it to validate my model on, to really check to see if my model is doing what it's supposed to do. And so all my training happens on the training data. And then validation is a way for me to compare models. I can compare models on the validation set and see which model generalizes to unseen data. And usually we can take validation accuracy as kind of our ideal metric to optimize. We want to have the highest validation accuracy because that tells us that our model is not just adapted to the data that we have, the training data that we have, but that it actually models the underlying physical phenomenon. So once we've done that, there's a lot of ways to do feature selection. There's something called greedy forward selection, greedy backward selection, many other ones, and then there's some metrics. But so greedy forward selection is it's the following scheme, and it's kind of naive, but it works well in practice. So the idea is to start adding variables one at a time. So I start with one variable, and then I create my linear model, use some metric that I evaluate the model on my validation accuracy, get some value for the validation accuracy or loss, and then add another variable to the model, get the new validation accuracy, compare it to my one from before. If my validation accuracy or my loss decreased, if my accuracy increased or my loss decreased, that tells me that adding the second variable was beneficial and that I should keep it in. And then I continue with the third variable. So I have my model with two variables, I add my third one, get the new validation accuracy, and then decide whether the third variable is worth keeping. And I keep doing this in a greedy fashion until I cycle through all my variables. Yeah?
What if, like, the first variable you get is like that?
If the first what?
The first variable you get,
Then try a different variable.
no, like, you say you check the second one, it's better, add it, right?
Yeah.
So how do you know if, like, this first one is, like, not beneficial at all?
I guess you never know. I guess you kind of have to play around for yourself and see if the first variable you're using makes sense to use. So greedy backward selection is kind of the opposite, where I start with all the features, all my predictor variables, and I greedily remove one at a time. And I keep removing them in such a way that when I remove it, if my model performance increases, then I leave it out. But if my model performance suffers from removing the variable, I should put the variable back into my model. And that's how those selection algorithms work. There's also something called, well, before I say what it's called, some of you might be wondering, is this the best way to do this? What if doing this in a greedy forward fashion is not the best way? What if there's some subset that I'm missing by doing this greedy forward selection that I'm missing that could, in fact, be the optimal combination of variables? And so there's something called recursive feature elimination where I kind of check all subsets of variables. And that's a lot more computationally expensive, but I guess a little bit more rigorous and believable. And so we'll do that in the demo, actually. So I have a model, but I need to have some way to measure my model, measure the goodness, some metric that I can use to compare models. And there's a lot of different metrics. So R squared is something you might have heard of. R squared measures the proportion of variability in the independent variables that's captured by the dependent variable. There's MSE, which stands for mean squared error, which is the sum of squared errors, like the sum of squared residuals that we've seen. Something called the AIC and BIC, which stand for Ikaike information criterion and Bayesian information criterion. Those concepts come from information theory and are pretty cool. And you can use those to do model selection also. But just to remind you, MSE looks like this. It's the sum of squared errors. The true value y minus y hat, my predictions. Square those, sum them up, take the average, and that's the mean squared error. Cool. So now you are all well versed in the basics of linear regression, linear modeling. But as I've continually said, this is only the very, very beginnings of what we can do with regression. And so there's a lot of generalizations that a lot of machine learning algorithms are based off of. So we can generalize regression from the continuous setting to the discrete setting and talk about classification. Models such as logistic regression, which we'll cover next week. Support vector machines, which will be covered in week 6, I believe. And then we can kind of stray away from this linearity assumption. It's kind of naive to assume that everything has a linear relationship in the real world. So it turns out that many phenomena are best described in a nonlinear fashion. So we can do nonlinear modeling So with a lot of different ways. We can do kernel smoothing, splines and generalized additive models, nearest neighbor models, a lot of nonlinear regression models. In fact, a neural network, which is something that the staff's very passionate about, can be thought of as a nonlinear regression model. We can talk about interactions. So tree-based models, bagging, random forests, boosting. These are just other ways to capture nonlinearities, as well as random forest being a very popular model that you might have heard of. That will be covered in week 6, I believe, or week 5, or something like that. And one other thing that's very, very widely popular used is called regularized fitting. So next week's lecture will cover a lot about regularization and what it really means and how it happens and what it does. But I just wanted to introduce you to the term regularization. And so we can talk about ridge regression or lasso regression, where we add some penalty to our cost function, j of theta, and then we proceed to minimize. So we can add, in the case of ridge regression, an L2 penalty, or for lasso, we can add an L1 penalty. But don't worry about that right now. Next week we'll learn more about that. So other just things that I thought would be interesting for you guys to be aware of as practical data scientists. I'm not going to talk about these, but I just wanted to tell you things that I've done that have been very useful and good to know. So polynomial transformations. So sometimes taking the square or the cube of my input data is more beneficial. Basic expansions, I can define my regression model in terms of an orthogonal basis. It's cool, it's useful, don't worry about it if you don't understand it. Dummy coding of categorical inputs. So just you should know how to input categorical variables into your model by doing dummy encoding. Time series models. I'm a huge fan of time series models, and a lot of data that we see is time series. Stock, prices, climate data, it's all time series. And so it's important to know how to deal with time series data, which in fact, by nature has a lot of dependence. There's dependence over time. And so this assumption of independence is completely thrown out the window in time series models. But it's a very, very interesting field and very widely used and fun. So we can talk about hierarchical modeling, which is where I have hierarchies and I model within hierarchies, and I get to find relationships that might be lost by looking at the whole population. Whereas if I look within different subgroups, I can discover more interesting relationships. And we can talk about, within that regime, we can talk about fixed effects and random effects, and it's a whole can of worms. One thing that is super, super important is causal inference. So when I teach linear regression, we don't even teach it to I teach that 20, and we don't teach linear regression like this at all. But when I teach the regression line, we teach at least what the line is. The most important thing, or one of the most important things I tell my class to take away is to do not confuse correlation with causation. I'm sure you've heard that before, but it's really important, the mistakes you can make if you start to confuse the two. So when we estimate these parameters are not causal. An increase in x will not cause y to change by this much. In order to make statements of causal inference, or of cause, statements of cause, there's a lot more stringent assumptions that have to be made, and a lot more rigorous framework that has to be put in place before we can make causal statements. But it's a very interesting field of study, and I encourage you to look into it if you are interested. And the last thing I think is interesting is spatial models. So you can imagine I have a heat map of the United States, and I have data within each region, and I'd like to make some models that are that can describe things within different spaces. So spatial models are cool too. And wow, this is all I had for the slides. So we'll have a demo, but for now, are there any questions? Yeah.
So you kind of just, so you mentioned that you can split your data set into the training set and validation set, but you didn't really go about explaining exactly what proportion you use, what sub, or what like part of the data set, because they could be,
Yeah. So the actual way to do that will be discussed in another lecture. There's standard ways, like maybe like a 70-30 split, 70% training data, 30% validation, 80-20, you know, it's a heuristic. And your answer might change depending on the size of your data. I blew through a lot of stuff in that 50 minutes. You can take 3 graduate courses on linear models to still not know everything. And so I really tried to cram a lot into an hour. And so I apologize if a lot of it didn't click. but I really hope I gave you not so gentle introduction to the intricacies of regression and I hope I kind of opened your eyes to how it can be thought of as fundamental for everything else that we want to do with more complicated models. Are there any other questions? Cool. So before I show you my demo, it's a pretty long demo with a lot of stuff, and I hope you'll get a lot out of it, but let's do attendance real quick. So the link for today is tinyurl.com/regressme-day3. So while you're filling out this attendance sheet, I want to take like a 5-minute break, and I really want you guys to talk to one another and find a project group. You'll be a lot happier if you find a project group before you leave this room today. So yeah, talk to each other, find a project group. You can stand up, move around, and we'll get back to the demo in like 5 or 10 minutes. Yeah. I'll come to you right now. Oh, okay. Let me change that. Sorry. There you go. Does it work now? Cool. Should work now. All right, we'll reconvene in about 5 minutes. Find a group. I'm serious. Find a group.
There's a lot of responses though.
Yeah, there's try refreshing the page.
Oh, I think there's two.
Really?
Well,
No, I'm fine.
you need to be signed into your Berkeley email. You guys are signed in.
Find the group. Find the group. Find the group.
Jordan, turn off the UC Berkeley thing.
Turn it.
Hey, again, I turned it off. Okay, really?
Name of the person.
Yeah, we'll be on there.
Yeah, make friends. Find a partner. Friends. Find a partner. All right. All right. All right. Let's get it. Okay. That's let's go back. All right, let's get back to the demo. All right. Has everyone found the group? No one's found the group. Great. I won't grade your project if you're not in the group. Find the group. Okay. So, Everyone's filled out the attendance form. Everyone's found the group. Life's good. Let's keep it rolling. If you pull the material for today, you open day 3. You see these 3 files. First one's the demo. Second one's the slides. Third one's some data, some NBA salary data. Let's open the demo, and let's do it. Day 3, linear regression. Let's get it. So we'll do some imports. These are some libraries that we'll use. So let me do a little. Oops. Okay, so the data that I'm going to read in is data from some MBA salaries. And the first thing I'll do is drop NA. So I'm deleting all the rows with missing values. And then I print the head of the data. So the head has 5 rows, and there's 22 variables, everything ranging from marriage status to wage, years of experience, age, education, number of games played, minutes played, what position they are, other stats, and other interesting things. Cool. So that's the data that we'll be using. And as someone who's used this data set before, I know that it's often useful to take the log of wage. And so what I'm going to do here is just make things easier for me and just extract variables from this data frame, NBA sals. And so I'm going to extract log wage, wage, points, and years of experience. Cool. So the first thing that I want to do is compare 2 simple linear regression models, where I pick one of my predictor variables, make a model, and figure out which model's better. So model 1 will be regressing wage on point scores, whereas model 2 will be regressing wage on years of experience. So let's first, before we do any modeling, let's plot scatter plots of what this data looks like. So here's the first scatter plot. It's wage versus points. We see that there might be some linear relationship that's overall positive. Here's a scatter plot for wage versus experience. Also, we see there's some kind of positive trend. But which of points or wage is a better predictor of, which of points or experience is a better predictor of wage? That's the question that I want to answer. And so if I were to estimate the regression lines and plot them, it would look something like this. So wage versus points with the regression line added looks like this. Wage versus experience with the regression line added looks like this. And let's see how I did this. So I first, I created an OLS object, ordinary least squares object, from the stat models package. So the way to do that is to write sm.ols and then give it the dependent variable, followed by the dependent variable or independent variable, and then fit it. And then I want to plot the points and then the predicted points. That will give me the regression line. And then I also want to see the original scatter plot. And I do that for both the predicting wage from experience and predicting wage from number of points scored. And so I get these nice looking plots. But which one's better? Which model is a better? Which model better explains the natural phenomenon of NBA players' wages? So as I mentioned before, one of the first steps that we want to do is to separate our data into a training and validation set. And so I think I did like an 80-20 split here, or a 70-30 split. And so I'm taking the first 214 data points to be in my training set. I'm taking everything else to be in my validation set. And I'm doing that for each of the variables, wage, points, and experience. So now I have a training and validation set. And so what I'm going to do now is train a model on the training data with each of the models 1 and 2, evaluate the model on the validation data, and then I can see how my evaluated model did and look at the mean squared error of that model on the validation data. And my conclusion will be based on the mean squared error. The model with the lower mean squared error on the validation data, I will conclude will be a better model. So the first thing we can do is regress wage on points. So the mean squared error for regressing wage on points is 0.448. Now if I regress wage on experience, the mean squared error is 0.5514. So the mean squared error for the first model was lower. And so I can conclude that points scored is a better predictor of wage than years of experience. And we just did our first linear regression. Yeah. It's going to get a lot crazier. Yeah.
Could you explain the third line, like the MSC equals 1 over?
Yeah. So that mean squared error is just the sum of the average sum of squared residuals. And so I'm just hard coding it. But you can also use sklearn's mean squared error function. But all I'm doing here is calculating the mean squared error. I'm taking the sum of the squared residuals and then taking the average of that. That's what this third line is doing. Cool. So I figured out which individual variable is a better predictor. But what's stopping us from using both in our model? Why would I not use both wage and experience to, or both experience and points to figure out wage? Or at least estimate wage. And so if I were to create a model that uses both experience and points to predict wage, and look at the summary of that model, it would look something like this. So you see all the coefficients and their estimated parameters. So the estimated parameter on experience is 0.0866. The estimated coefficient on points is 0.1016. And you get some nice other statistical properties about those estimates here with this OLS summary. Let's visualize this though. So again, what I'm doing here is I'm creating a model that takes into it a player's points and years of experience and will output an estimated wage for that player. So let's visualize this. In this case, our model is going to be in 3D, right? Because I have two predictor variables. When I had one predictor variable, I had a 2D model, one scatter plot in 2D with a line going through it. In 3D, my line of best fit is actually a hyperplane. And in fact, this is true in n dimensions. The line of best fit is actually a hyperplane in n dimensions, or p dimensions, the dimensions of your variables. Cool, so if I plot this in 3D, I get something like this. So here I have a hyperplane in 3D that describes the relationship between experience, points, and wage. And so this plane is the plane of best fit. And so the plane is my function. I input it into it a experience and some points, and the plane will tell me the estimated wage for that player. Cool. So now I want to talk a little bit about residual analysis, something that we talked about during the lecture, but we didn't get to really touch upon yet. So I want to look at the residuals of this model so I can determine whether my model was worth using. Are the assumptions that I made validated here? So let's look at the residuals. So the first thing I want to do is predict wages from the data that I have, and I can get y hat. And then my residuals are just the true value minus the predictions. So wage minus wage hat. Okay? And then I can make a plot of y versus the residuals. And so if I plot y, or in this case I did residuals versus y, doesn't matter, I see some pretty nice things. I see that there's no trend, which makes me believe that the linearity assumption is satisfied. I see maybe a little bit of heteroscedasticity, but not too much to worry about. Most of the residuals are randomly dispersed with more or less equal spread across the x-axis here. And so this is one of the first diagnostic plots that we would look at to check our assumptions. We can also make a histogram of the residuals to check the normality assumption. And more or less happy. So this red curve I drew on top is what a normal curve would look like if the data was indeed, or what the histogram would look like if the data was indeed normal. And so you see that the red line kind of overlays the histogram almost perfectly, which allows me to believe that the normality assumption is pretty satisfied here. So regression is a good choice of modeling. Cool. So now I want to kind of get a little bit more advanced and talk about feature selection. So in the last part of the lecture, we asked ourselves the question of, if I have so many predictor variables, how can I begin to choose the best ones that make my model the best, that allow me to best approximate the underlying natural phenomenon? It could be that just because I have so many features, it's not necessarily true that inputting all the features into my model is going to give me the best model because it has the most information. In fact, there could be a lot of noise, a lot of redundancy, a lot of things that I don't want in my overall model. And so it's important to figure out how to choose the best features for the model. Yeah.
But in what scenario would too much information be detrimental? Because you can just set the coefficient of whatever that variable is to 0.
Yeah.
The machine should be able to figure that out, right?
Yeah, exactly. That's exactly what happens. So when I have something called collinearity in my data, which means that my data is redundant, some two variables are redundant. In fact, the estimation procedure will kind of force one of the estimated parameters to be 0. And so the model does, you're right, take care of that, but there's no reason for us to even input it in the first place. It's just a waste of computational resources. And then that makes a difference for when we're talking about big data. Maybe for this small MBA salary data, we don't care too much, but it's important to not be wasteful. So let's talk about how we do this. So I'm going to use this package, or this function called RFECV, which stands for Recursive Feature Elimination with Cross-Validation. Don't worry if you haven't heard of cross-validation yet. It's one thing that we use to choose our model parameters and to evaluate our models. We'll talk more about that in subsequent lectures. It's a more complicated methodology as to how we split our data into a training and validation set. It's just a fancier way of doing that. Works better. Cool. So let's see what columns we have to work with. What are the variables I have available for me to choose from? So here are all the ones I have. I have whether someone's married, their wage, or I'm going to predict wage, but I have experience, age, years of education, etc. Whether they're African American or not, what position they play, stuff like that. So I have 20, and overall I have 20 odd features that I can choose from. And using all of them is naive. So I should figure out what the best combination of them is. And with this function, RFECV, I can specify the max number of features that I want. So just for this example, let's pick a subset to work with. So maybe I'll pick these features to look at and then pick any subset of this, any combination of these features that gives some nice properties. So I'm going to pick experience, games, minutes, whether a player is a forward, center, or guard, number of points scored, and then their age. And I'm going to also add a constant to that. So remember, kind of my first step is adding my x0 term, my bias term of 1. So this function sm.addConstant adds a column of 1s to my data, which is important not to forget. Cool. So now that I've done that, I can do the following procedure. I can define a linear regression object from sklearn. I can invoke the function RFECV, plug in my linear regression object, tell it to take one step. That's some parameter. I forgot exactly what it means, but it's in the documentation. And then tell it to perform 5 folds of cross-validation. And then I can fit it to the data that I want to fit it to. So I can give it the data with these 8 variables to choose from, and then I want to predict wage. So that's what I'm specifying here in the fit option. So if I run this, oops, I need to run the above line first. My RFECV spits out the best features that I should use. I should use the first one, the fourth one, first one, 5th one, 6th one, and 7th one. Those are the best features that yield the optimal performance here. And I believe the metric that they use to determine which model is better, I think they do some kind of mean squared error criterion, something that we talked about. Yeah.
Why do you pick some subset to run this on this running level data?
Because I didn't feel like it. There's no reason why I didn't pick run on the full data set.
So, even if this was modeled correctly, it might be neglecting some variables which are crucial.
Totally, yeah. Could be doing that. I wanted to do this very quickly, and so if I maybe had the full data set, the number of subsets would grow very expansively. And so I really just wanted to have this quick for demonstration purposes. So as you can imagine, the subset selection procedure can be very expensive, especially when I have a ton of data and a ton of features, right? There's so many different, if I have 1,000 predictor variables and I want to choose any subset of 5, I'm looking at 1,000 choose 5 number of models, and that's just a huge number of models to evaluate and test, and That's not feasible. And so that's why, even though this subset selection method may be the most sensible, it might not be practical when I'm actually dealing with big data. But now that I've chosen the variables that give me the best model, I can evaluate it and then look at my MSE. So here's the model, the best model. Those are the coefficients on the best variables, and then I can evaluate the best model. So the first thing I'll do is I'll split it into a training and validation set, like I always do. Fit the model to the training data, evaluate the mean squared error on the validation data, and I get that the MSE of the best model is 0.33. So if we scroll up, the MSE of our other models were, I believe they're 0.45 and 0.55. Now with our recursive feature elimination, we were able to get the MSE down to 0.33. So because our MSE is much lower, we can say that this model is better. Cool. Any questions so far? Yeah, yeah. Make sure you run the chunks in order. My guess is that you may have run the chunks out of order. So I'll take more questions, but I just want to give you a peek about what we're going to talk about next. Kind of more advanced topics, some things that are actually probably used in production, so polynomial regression, something called an elastic net, which is a combination of different regularization techniques. These are kind of more advanced linear models that are very easy to implement in Python, but I wanted to show you them and show you how they compare with our standard models, because those are things that you'll see companies actually using, something like an elastic net. Cool. Any other questions? We're doing great on time, guys. We got plenty of time, so let's have a little dialogue. Or you can ignore me, and I can talk to myself. It's okay. Don't feel bad for me. So I take it that you guys all understand linear regression perfectly, and that you're all masters at implementing it with sklearn and stat models. Experts. I have a crowd full of experts. I should just go home. This girl in the front told me, "Okay, bye." Let's talk about polynomial regression. So I'm going to import these things from sklearn that make computing polynomial features very easy. So from sklearn preprocessing, import polynomial features, which is a function that can actually take in a data frame and input and output the data frame with polynomial features, with squared values of the original data, or cubes, or whatever polynomial degree you want. And then rather than keep having to define my MSE function, I can just import it from sklearn and use it like that. So now I'm going to talk about a new data set. It's also built into sklearn, called the linerud. And I'm not actually sure what linerud means, but it's a sample of data of men and some variables that are measured from their physiological features, and there's some labels for them as well. Maybe weight or blood pressure or something like that. Yeah.
Just to go back to like the area that you brought up, a lot of us are getting it. I don't know, like, yeah, so we put it on that, so that's what it's okay. I was just saying that like when we tried to index in the NDA underscore dot with like that array was not in the index.
Something I can think of perhaps is that our pandas versions are different. Are you using Python 2.7 maybe? How many of you are getting that error? Oh, wow. My crew's on it, so just hang tight. Sorry about that. So if I want to do polynomial regression, I can kind of set up a pipeline. And the pipeline will take in data and the degree of the polynomial features that I want to compute. So I take in input data x, output data y. I add a constant. That's the first thing I do is I add a bias term. I then create polynomial features. I split my data into a train and validation set. I fit the polynomial regression model by feeding in the polynomial features into a standard OLS model. I make my predictions on my training and validation set, and I return the MSEs. So this is the pipeline that can do everything that I want end to end, rather than keep having to do things individually. I can just give it data, different degrees, and figure out the best model. So now I want to test different degrees of features. So I want to test degree 1, 2, 3, 4, 5 features. So I'm going to try different order features and figure out which polynomial degree is the best. And remember, I'm going to use best by looking at mean squared error. So I'm going to define best as having the lowest mean squared error. And so if I implement this polyreg pipeline for all the 5 degrees, oops, I need to run it first. I need to load the data. I need to do something else first. I need to do my imports. Don't forget your imports. And then I can get results from my different experiments. So we see that it looks like degree 2 probably is the best polynomial feature degree. When I compute second order features, I get my train MSE is pretty low, and my validation MSE is also pretty low. When I compute higher degree features, like 3, 4, 5, you see that my training MSE is essentially 0. When I compute higher order features that are that high, I can perfectly fit my training data. But what I'm doing there is fitting the data that I have and not actually fitting the underlying phenomena in nature. I'm overfitting to my training data. And so just because my training MSE is essentially 0 for higher order degrees, that to me doesn't mean anything. What I'm really concerned about is my validation MSE. That tells me how well I'm able to generalize to the real world, whether or not I'm just overfitting to the data that I have. And so always look at your validation metrics, because those are going to be a lot more indicative of good. Okay, so once I've done that, oops. So I can make a plot, and the plot has on the y-axis the log of my mean squared error, and on the x-axis has the degree of polynomial features, and I can plot both the training and validation MSEs. And I can see that even though train MSE constantly decreases, or it doesn't always decrease, but it decreases as the degree increases, my validation MSE in fact starts to increase after a certain degree, because as my degree gets high enough, I'm overfitting to the training data, and the model's not able to capture the information in the validation data. And so my conclusion would be to use degree 2 features here. That to me is the best model at this time. As you'll soon learn, you're never done doing model selection. There's always a better model. It's up to you to decide when to stop. Cool. Any questions about that? Yeah.
So we're fitting a problem when you're interpolating in the same range of data?
Yes. The question was, is overfitting a problem when you're interpolating within the range of data that you have? And the answer is yes. And we'll talk more about why in the next, or 2 weeks from today. Lecture 5 will talk about the bias variance trade-off, something that's very important. Yeah. Yeah, so question was, what is overfitting? And overfitting is when my model is so well fit to the training data, but its performance on the validation data is trash. The model is so adept to fitting the training data that it loses the overall trend in the population level data. So that's what overfitting is. When I model my data too well on the training data, but I ignore the natural phenomena. And so it's important to figure out a careful balance between overfitting and underfitting. That's a common theme that as data scientists will encounter over and over again. And lecture 5 will talk more about that, the trade-off between the two. Any other questions? Yeah.
If you go back up to where you selected the subset,
Uh-huh.
you selected forward, center, and arc, right?
Uh-huh.
These indicator variables for looking at forward, center, and arc.
Yeah.
Is it one of them a linear combination of the other two?
Sorry?
Is it one of them a linear combination of the
They can't be linear combinations because they're one-hot encoded.
Which do you think are linear combinations?
Forward, center, and north.
So it may be redundant to include all three. Maybe I should only include two. Including two may be enough, unless there's a fourth position. I forgot if there was a fourth position. Okay, yeah. So then you're totally right. It's unnecessary to include all three positions. By including two of the variables, you're implicitly including the third one.
Right. I think my question was basically with the linear regression function.
Would it what?
With the linear regression function.
Yeah, it's nothing that you have to worry about. But it is good that you caught that. That's a good skill to have. Any other questions? Yeah.
How do you decide which data is for training and which data is for validation?
Yeah, so the question is, how do I split my data into a train and validation set? Which part of my data goes into which set? And before we do any of this, one fundamental assumption that we all make when we do cross-validation that we never think about is the assumption of exchangeability. We assume that all of our data is exchangeable, that if I train on some of the data, that it doesn't matter that I train on this subset rather than that subset. The signal is more or less uniform within my data set. And so I assume this exchangeability, which allows me to separate my data into two different sets. And so how I actually choose the two different sets there's actually a lot of ways. So standard is to pick like a 70-30 split, where I pick 70% of the data to go in my training set, 30 in my validation set. Maybe I can do 80-20, 75-25. It's all a heuristic. And to actually put data into that set, I just randomly pick it. I just randomly split the data. That's all, randomly. That's to answer your question, randomness. Cool. Elastic net. Don't worry if this scares you. So all it is the familiar objective that we're used to seeing from the lecture. And I added two regularization terms, an L1 term and an L2 term that we'll see more about next time. So if I just had the L2 term, this would be called ridge regression. If I just had the L1 term, it would be called ELASA. When I include both of them, it's called an elastic net. And it turns out that using both of them is often very advantageous. But the objective looks like this. I'm not minimizing theta, or I'm picking theta, which minimizes this function. And so I have these two penalties. And what those penalties do is encourage my thetas to be smaller. It's also called a shrinkage estimator. I'm shrinking my thetas. But I don't want to get into that too much because Neil's going to talk a lot about that next week. So same idea, except now I'm back to my NBA data. So elastic net's readily available in sklearn. So from sklearn.linear model, import elastic net. Create my x and y's. So I'm going to use all the 21 predictor variables, and my y is going to be the wage variable. And just as I did for the polynomial regression, I'm going to define a pipeline. And the pipeline is going to take in x and y. It's going to change them to empty arrays. It's going to add a bias term. I'm going to split the data into a training and validation set. I'm going to fit the elastic net model with the parameters. So the hyperparameter here that I'm using is alpha. Okay, so alpha is just a hyperparameter that I'm using. Just like the degree of the polynomial features was a hyperparameter. Alpha is something that I can choose on my own. The model doesn't learn it itself. And so there's a trade-off between higher and lower alpha that we'll see in a second. But I feed in this alpha into the elastic net function. I give it the L1 ratio, another hyperparameter that I'm not going to worry about. And then I fit it to the training and data. So dot fit x train y train fits the model to the training data. Once I fit the model, I have my estimated parameters, and I can make predictions. So I predict my validation data, I predict my training data, I evaluate the mean squared error on those predictions, and I can see what I have. So now I'm going to see how this elastic net changes as I choose different alphas. So how does my validation MSE change as I change alpha? So that's what we can see now by evaluating this on different alphas. So I'm choosing alpha equals 0.0001, 0.001, etc. These are the alphas I'm choosing to test my model on. And so if I do that, I see the following. I see that it looks like to me either alpha equals 0.01 or 0.1 are the best alphas. And I say that because you see that my valid MSE is the lowest for alpha 0.1. It's lowest here. But it's almost the same in alpha equals 0.01. And I think I like alpha equals 0.01 better because the training MSE is much lower. So I know before I said we don't care about the training MSE, but I still like it to be low, right? I'd rather it be low than high. And because the difference is so marginal between 0.01 and 0.1 for the validation MSE, I think you can make an argument for both ways, but I would say that alpha equals 0.01 is the best alpha to use here. And something else that we see that's pretty cool is the MSE is so low. The MSE is 0.15. For all our previous models, for the subset selection, for the simple linear regression, for using just points or experience, the MSEs were like 0.55, 0.45, 0.35. This elastic net model is pretty powerful. Regularization is pretty useful. The MSE is much lower. And so that's why I really wanted to show you guys elastic net and how it's pretty cool. And so now I can make the same plot where I plot the MSEs for the training and validation sets against alpha to show you how alpha affects the MSE. And so you see that as I first increase alpha, the valid MSE decreases, but then as I start to increase alpha, the valid MSE starts to increase again. And what I'm looking for is kind of like the elbow in this curve, so the lowest point on the validation curve. So this is alpha equals 0.1, and that has the lowest valid MSE. But then I said before that 0.01 might be better, even though the valid MSE is a tidbit higher. And so that's how I can go about choosing hyperparameters. I can try different hyperparameters, evaluate the model on the validation set, and then I can choose the model with the hyperparameter that gives you the best validation MSE. So that's a little story about how I do model selection. How do I choose the degree of my polynomials? How do I choose the alpha in my elastic net? How do I choose what features to use? And the scary thing is that we did all these things independently. I could have done an elastic net with polynomial features with subset selection, and we'd be here all day. And what's even scarier than that is I haven't even began to touch all the other things that we could do. But I don't know if scary is the best word. I think it's exciting. So again, the goal here for today was to show you all the cool things that you can do that are actually practical. Some of the more advanced models that are actually being used in industry are pretty easy to implement. And so it's up to you to do the following as data scientists. It's up to you to, first of all, make a model that you can think for yourself would make sense. If I were to think through the model that I'm making, it doesn't make sense to predict that from that. It's up to you to go about choosing the best model. And with that, that involves feature engineering, choosing what features to use, choosing your hyperparameters, a lot of other things that go into model selection. Things that were touched upon in the lecture and things that I've showed you today with these graphs. So these graphs are actually very nice. They show you visually how to choose the best hyperparameters, which in hyperparameter choosing is a very important topic in machine learning. It can make or break you. Changing your hyperparameters ever so slightly can drastically influence the performance of your model. And so that's why it's important to be as rigorous as possible in making sure that the hyperparameters you choose are the best ones. And again, the way you do that is by doing cross-validation, looking at your cross-validation scores on data that hasn't been trained on, and then choosing the model that generalizes best, that has the lowest mean squared error. So again, I apologize for going so fast over so many different things. It'd be impossible for me to go slowly and cover the stuff that I did. I didn't even begin to touch half the stuff that we could have talked about. But I hope now you're all aware of linear regression, optimization for linear regression, model selection, model estimation, model testing, things that are fundamental to understand as data scientists. And this idea of regressing on a variable is so ubiquitous in everything else that we'll do for the rest of the semester. And so I really hope today, even though it might have been one of the more simpler models, it's definitely one of the most powerful and I think one of the most important. So that's all I have for you today. Just two quick announcements. Homework 1 is due tonight at midnight. Project 1 was released and is due in 2 weeks. you need groups of 3 to 4. That's strict. And yeah, thanks.
We have office hours until 8.